Hi everyone, welcome back to the Banach Spaces webinar. Today we are very pleased to have Bence Horváth from Czech Republic. He's currently in the Czech Academy of Sciences as a postdoc there. And he's speaking on when are surjective algebra homomorphisms of B of X automatically injective. Bence?
Thank you very much, Benjamin, and thank you very much for the invitation and organizing this seminar. I think it's been already said, but I have to repeat that I certainly haven't been able to attend so many good talks in one calendar year. That's very, very unusual. So thank you very much for this. So today I'll be speaking about something that I started working on as a PhD student of Yeman Choi and Niels Lausen. So definitely a big shout out to them as my PhD supervisors. And the second half or some parts of the talks are current recently submitted work joint with Tomáš Kania. I don't know if he's here. So throughout this talk, when I say Banach space, I will mean a complex Banach space most of the time. It won't make much of a difference. When it does, I'll let you know. And the script B of X will just mean that this is the unit of Banach algebra of all the bounded linear operators on X. As a motivation, let me give you a theorem of Idelheit from the 40s. So when you have two Banach spaces, then they are isomorphic to each other if and only if B of X and B of Y are isomorphic. What do I exactly mean by that? I mean that X and Y are linearly homeomorphic if and only if B of X and B of Y are homomorphically homeomorphic. So this is just to make sure that I'm not assuming any isometric property at any point, but when I do, excuse me, then I will explicitly mention it. And when one stares at the proof of this theorem, it's not entirely obvious where, for example, the injectivity part was used. So it's a sort of natural question to ask, maybe naive, but quite natural, that can we just drop this assumption? So more formally, if we are given X and Y Banach spaces and there is some surjective continuous algebra homomorphism between them, is this automatically injective? And of course, we know that the, sorry, can you see the top of my screen? Because I have it blocked somehow. Is it all right for you?
The top line says, yeah, in general, the answer is no.
Okay, thank you. So in general, of course, the answer is no, because we know that there exist Banach spaces such that B of X has a character, such that there exists a unit or therefore necessarily surjective and continuous algebra homomorphism to the complex numbers, and of course just use the stupid isomorphism between complex numbers and their algebras of operators. And this is of course not injective. Just to remind everybody here who might not be that familiar with these things, that sort of some classical examples of spaces with characters include the first one, I guess, was the James space, P equals 2, or the other James spaces satisfied is the so-called what I'll be calling Samadani space. This is continuous functions on the ordinary interval 0, omega 1. Or take your favorite hereditarily indecomposable Banach space, of course. And you can get different examples by having Banach spaces with algebras of operators quotient onto some commutative complex Banach algebra. Again, one probably not that well-known one is this so-called Mankiewicz space, separable superreflexive. This is B of X quotients onto L infinity, or take Gower space, or Matthew Tarbard constructed an indecomposable but not AGI space which quotients onto L1 of natural numbers including 0, or the space is constructed by Motakis, Puglisi, and Zisimopoulou, and the so-called Koch-Mitter spaces as well. So these are just examples. We'll get back to it later. But for some classical spaces which are not that pathological, let me say, The answer to the question is yes. So for example, take a separable Hilbert space and take Y to be any non-zero Banach space and take any continuous surjective algebra homomorphism between them. But I would like to show that this is manifestly injective as well. So we know that by Calkin's result from the 40s, the ideals, the lattice of close two-sided ideals of B of H is completely described by this chain. And because the kernel is of course closed, it must be one of these three things. So we either have it that it's trivial, it's zero, or we have it's the compact operators, or it's the whole thing. And I would like to exclude these two cases. Of course, the third one is immediately, that's just not possible because our map was surjective and Y was non-zero. For the second one, I'll show that I cannot hold either, because if it would, then you had that the Calkin algebra is isomorphic to B of Y. Now, there are many ways of seeing why this can't possibly be true. Just here's one. Assume for a moment Y is infinite dimensional. Then you have that B of Y is not simple as an algebra, simply because you have the norm closure of the finite rank operators, the approximable operators, which is a proper close two-sided ideal, of course. But because this is a maximal ideal in B of H, which is equivalent to saying that the Calkin algebra is a simple algebra, this cannot happen, it's a contradiction. What if Y is finite dimensional? Well, that's not possible either, because B of Y is finite dimensional, but the Calkin algebra is known to be very not finite dimensional. So the only thing we're left with is that the kernel is trivial, which is the same as saying that psi is injective. So we can actually replace this H with C0 or LP spaces for the moment P not including infinity, because of the by now classical result of Goldberg, Marcus, and Feldman. They have proved that the lattice of close two-sided ideal of B of X is given exactly by the same chain as for any separable Hilbert space. So you can just run the same argument and it will work. So it's worth now making a definition to capture this property. I'll say that a Banach space has the Chi property if whenever there is a non-zero Banach space Y given and the surjective algebra homomorphism from B of X to B of Y, then it is actually automatically injective. Chi just stands for surjective. Surjective homomorphisms are injective. If you notice that I didn't have the continuity assumption here, that's because you don't need that, that's automatic. It follows from work of Barry Edward Johnson that if you have a Banach algebra A and Y is any Banach space, you have a surjective algebra homomorphism from the Banach algebra to B of Y, then this is automatically continuous. Of course, Barry Johnson proved this in much greater generality, but for our purposes, this is sufficient. So from now on, I will, when there's a surjective algebra homomorphism, I'll not mention any continuity because it's automatic. So what does this Chi property say? This says that if X is a Banach space with this property and Y is some non-zero Banach space such that you can find a surjective algebra homomorphism from B of X to B of Y, then B of X and B of Y are actually isomorphic as Banach algebras, which we know that by Ideal-Heit's theorem is the same as saying that the Banach spaces are isomorphic to each other. So this has to do with isomorphic properties as well of the Banach space. So let me just recall that we know now that because of the Marcus Goldberg-Feldman theorem that C0 and LP have the Chi property for P in the reflexive range and P equals 1. And it's quite natural to ask that what will happen if we look at L infinity. The argument I try to outline above will of course not work. I mean, that was very pedestrian. I just did step by step, went through the ideals. We cannot do here because we know by quite recent work of Bill Johnson, Gilles Pizier, and Gideon Shechtman that the lattice of the closed two-sided ideals of B of L infinity has at least continuum many distinct ideals. So, well, just let me put forward that the answer is, does this space will still have the Psi property, but we will have to do something else. Let me remind you just a very easy standard little fact that it's sort of a dichotomy result that if we have X and Y non-zero Banach spaces and there is some non-zero continuous algebra homomorphism from B of X to B of Y, then either this map is injective or its kernel is large enough to contain the approximable operators. Again, approximable operators is just an operator non-closure of the finite rank operators. We can strengthen this slightly when psi is surjective, but for me to make sense of the statement, let me just remind some of us what the ideal of the inessential operators is. So we will say that T is inessential if the identity minus ST is a Fredholm operator for every S, or equivalently the dimension of the kernel of this operator and the dimension of the space modulo the range is finite dimensional. This is, so the set of the inessential operators will be denoted by the script E of X, and this is a proper closed two-sided ideal whenever X is infinite dimensional. In general, just where to put this ideal, so for any infinite dimensional Banach space, this is a sublattice of the lattice. The lattice is usually much more complicated, the lattice of ideals, but this is a sublattice, and this is a proper inclusion. This may or may not be. This may or may not be. This is the strictly singular operators. This again may or may not be, and this is a strict inclusion. Just I cannot help mentioning it, but Valenta Ferenczi recently proved that because it was conjectured that this script E, which is an operator ideal in the sense of Peach, it was conjectured that this is actually the largest proper closed operator ideal. And Valenta showed that this is not only not true, but there is no largest proper closed operator ideal in the sense of Peach again. So let me just get back to the result that I wanted to present. This is the cornerstone of many of the arguments. So if we have X and Y non-zero Banach spaces and the surjective algebra homomorphism between B of X and B of Y, then this psi is either injective or the kernel contains the inessential operators. So if it's surjective, we know that not only does it contain this, the approximables, but also the inessentials. Of course, these may very well coincide, so it's not always very helpful, but it's formally at least something more. But with this, we can actually show that L infinity and Schlumprecht's arbitrarily distortable Banach space do have the Psi property. Let me just mention before I get to the sort of sketch proof of this theorem why something that is helpful. So if X is a Banach space that has a complemented subspace which is isomorphic to X squared, then having the Psi property is the same as only considering infinite dimensional Banach spaces in the description of the Psi property. So if X has the Psi property, then for any, that's equivalent to saying that for any infinite dimensional Banach space Y, any surjective algebra homomorphism from B of X to B of Y is automatically injective. So so why is it true? It's because if X is a complemented subspace isomorphic to X squared, then simply B of X cannot have finite codimensional proper two-sided ideals. We don't even not only closed, but any algebraic ideal. So how to prove this theorem? So take Y infinite dimensional, sorry, I forgot that here, and take a surjective algebra homomorphism. And assume towards a contradiction that this is not injective. And we know from this dichotomy result that I put up there that the inessential operators must be contained in the kernel of psi. Let us consider first a case where X is L infinity. It was characterized, I think, sorry, it was proved by Niels Lautzen and Eric Loy, I think in 2003 or 4, that these ideals coincide with each other, and they are the unique, and it is the unique maximal ideal in B of X. So the inessential operators, the strictly singular operators, the weakly compact operators, and the operators with separable range coincide, and it is the unique maximal ideal in B of X. So because of this containment, and we know this is a proper ideal, we know that they must be equal to each other. Okay, let this put on a shelf for a moment and consider Schlumpfrecht space. This has the nice property of being complementarily minimal, by which I mean that if you have any infinite dimensional subspace of it, contain further subspace that's complemented in X and isomorphic to it. So we know by an old theorem of Whitley that the strictly singular operators must be the unique maximal ideal in B of X. Consequently, we must have that it coincides with the inessential operators, and it must be the kernel of psi. So in both cases, we could conclude that the kernel of this map psi is actually the inessential operators. So we have that this quotient is isomorphic to B of Y. But recall that this was a maximal ideal. So again, we have something on the left-hand side which is simple, and something on the right-hand side which is not simple, because Y is infinite dimensional and has some ideal. This is a contradiction, so we know that psi must be injective. Now, this is, as you see, it's not something overly sophisticated, but it captures many times that even though we know that the lattice of the close two-sided ideals of L infinity is very complicated, we don't need to worry about the small ideals in the terminology of Bill and Gideon and Gilles. What I would like to do, and at least some part of the rest of the talk, is to show that for some other natural Banach spaces, show that they have the Psi property. Firstly, I would like to consider the C0 and the L1 sum of finite dimensional Hilbert spaces. You probably do know that the lattice of the closed two-sided ideals was characterized here as well by Niels and Charles Reed and Thomas Schlumpfrecht and András Zsák and Rick Loy, I think, but I will flesh that out later. And also we can consider the long sequence spaces, and we can show that they all have the Psi property. Let me just remind you that this Banach space is defined to be that subspace of the L infinity on lambda, where lambda is some infinite cardinal number which has countable support, where the elements have countable support. Not only is this a closed subspace of L infinity lambda, but it's actually a sub C-star algebra of the commutative C-star algebra L infinity lambda. And you can show, it was actually, I think, first showed by Bill and Tomac and Gideon that this can be realized as a CK space. So another ideal, if you haven't seen enough already, that we will be considering is this so-called ideal of operators that approximately factor through another Banach space W. So if X and W are Banach spaces, we consider the closed linear span of the operators of the form ST. T goes from X to W, S goes from W to X. This is a close two-sided ideal, of course. And we will be particularly interested in the case where this W is isomorphic to some complemented subspace of X. In this case, if we take an idempotent with range isomorphic to W, then this ideal here coincides simply with the close two-sided ideal generated by this projection P, or idempotent P, I'm sorry. And there was this dichotomy result I mentioned before. There is a sort of analog for this, analog of this with this ideal, which says that if we have Banach space and a complemented subspace, and we know that this complemented subspace W has the psi property, then given any surjective algebra homomorphism from B of X to B of Y is any Banach space, then this surjective map must be either injective, or the kernel is so large that it contains the ideal of operators that approximately factor through X. This is, again, I think, not a very complicated proof, so let me maybe guide you through it step by step. It's probably worth. So suppose we have this idempotent with range being equal to W, the complemented subspace, and assume towards a contradiction that psi is not injective. Let us observe that it's enough to see that P is in the kernel of this surjection. Of course, that's just because the ideal of operators which approximately factor through X is just the ideal generated by P. So it's certainly because the kernel is an ideal. So assume towards a contradiction that P doesn't belong to the kernel. Then we know that Z defined as the range of this psi P is a non-zero, closed, and of course complemented subspace of Y. It's very important that it's non-zero. So we can make sense of a map defined from the bounded linear operators on W into the bounded linear operators on Z. Again, Z was this. It's defined the following way. You take some operator T on W and compose it with the projections on both sides. Here, this means that I consider the projection going from X, but I restrict it to its range, W. And hereby, I mean that I restrict it to the range and consider it as a map into X. So I can take the psi of this, and then I can restrict it to the range. So this is a well-defined map. It's very easy to see that it's an algebra homomorphism, and it's still quite straightforward to see that it's surjective. So again, we don't need to worry about any continuity here. It's fine. Now, because we assume towards a contradiction that this Z is non-zero, and we knew that in the hypothesis that W has the psi property, we know that this map must be actually injective. So that means that if you give me any bounded linear operator on X, such that it belongs to the kernel of psi, then we can consider the following operator. So this is just composing with the projections on both sides. I just apply the definition of this theta here. Notice that what we have here, this operator and this operator, this is just P, this is just the projection itself. And then we're using the size homomorphism, so we can factor it. But we know that this is in the kernel, so this whole thing is zero. Okay, cool, what does that say? By injectivity of theta, this says that this operator, this is zero, or you can again compose it from P both sides, and it gives that this operator PAP, this corner, this is zero. And we just will apply this in the specific situation where A is a very simple looking operator. Let us choose a norm 1 vector in the range of P, so this is just W, and norm 1 function with Banach such that it evaluates at 1. Because we assume that psi is not injective, we have, of course, that this rank 1 operator must belong to the kernel of psi. So by this, what we did above here, so you just put this operator instead of A, we know that P applied to this rank 1 operator applied to P is just 0. So if I applied it to the vector X, this must be still 0. I just write it down what it means and use the fact that X was from the range. And I use that this evaluates at 1. So I have that X must be 0, which is a contradiction because it was a normal vector. So we conclude that in the very beginning of the proof that P must be in fact in the kernel. And that was easy. That was enough to prove the claim. So we'll be using this in the following in different ways. Firstly, I will present quickly the proof of the facts that this Banach space, the Y sum of finite dimensional Hilbert spaces, where Y is C0 or L1, has the Xi property. The main ingredient of the proof is these results of Laussen, Loy, Reed, and Laussen, Schrumprecht, and András Zsák. And the result says that if you take one of these Banach spaces, then the lattice of closed two-sided ideals is given by this chain. The C0 case was done by these three, and the L1 case was done by these three, I believe. I hope I'm not wrong about this, but they'll surely correct me. So, and then what you do in the proof now, they just apply this dichotomy result I put up, and that will tell you that, well, Y is C0 L1, so it must have a Xi property. So if you have any surjective algebra homomorphism, which is not injective into any B of Y, then the kernel must be this or this. Well, it can be this. So it must be this, but this is the maximal ideal. And again, then you have something like a simple thing is isomorphic to a non-simple thing, and that just can't happen. So this was not the original way how I have proved this theorem. So because this dichotomy lemma actually, well, we actually only thought about with Tomek Kanya for our recent paper, and this was in my solo paper, and the proof was quite different. I was still using the ideal characterization, but I had to actually go through all the ideals here, and what I had to do is, when considering that which of these ideals can the kernel be, and I wanted to exclude the compact operators. So what I did there is argued that the Kalkin algebra of X cannot have minimal idempotence. I'm not going to define them here because I'm actually not going to use them. But this is just a, so why is it not Horváth Kanya, and why is it just me? Because it's an older result, just proved in an easier way. So recall that we know now that C0 and all the LP spaces have the Xi property. What about the non-separable versions? So what I was able to do in the first paper is I could show that all the non-separable Hilbert spaces have the Xi property. But the proof was very much relying on spectral theory. So because I use spectral theory to show that when you take any closed two-sided ideal in on the bounded of the bounded linear operators on non-separable Hilbert space, then the idempotence from here, sorry, from the quotient can be lifted to idempotence here, and then with some other machinery, one can easily see that this actually implies that this quotient cannot have minimal idempotence. And then one argues that if you could have a surjective non-injective algebra homomorphism into some B of Y, Y is infinite dimensional, then you would have an isomorphism of these two guys. And this one doesn't have minimal idempotence, whereas this, of course, has many minimal idempotence, because in B of Y, the minimal idempotence are precisely the rank 1 idempotence. So that was the original argument, and we were trying with Tomek for a while to try to somehow adapt and see if we can do this for other LP spaces. We can do a similar argument, and then we've been agonizing over this for quite a while to no success, but eventually we managed to do it in a different way. So the result is that we did with Tomek, that if lambda is an infinite cardinal, then any of these 3 guys has the Psi property. Notice though that P equals infinity. I have no idea about that. I have absolutely no clue if that's true or not. I think I would like to go through some of the steps, how the proof of this result goes, to give you a flavor, but that will involve telling you a bit of background material. I would like to define what the Y singular operators are on a Banach space X. So if X and Y are Banach spaces, then this subset is defined. Actually, it's easier to define what doesn't belong to this set. So T is not a Y singular operator if you can find a subspace of W, a subspace of X, is isomorphic to Y, such that T restricted to this subspace is bounded below. And so this set descript Yx is called the Y singular operators on X. Some simple facts. This set increases if you have increasing, if you consider increasing Banach spaces Y and Z, and also that it's sort of closed under multiplication from elements of B of X. So if A is a Y singular operator and T is just any bounded linear operator, then both AT and TA belong. They will both be Y singular operators. However, in general, this is not closed under addition. So in general, this set is not an ideal. We know though that it still has a convenient property, namely that if you consider the X singular operators on X, and if it's closed under addition, so we know that it is an ideal, and X is in additional something called complementarily homogeneous, then it must be the unique maximal ideal in B of X. I mean, this is a folk result, I'm sure, but we just included it in the paper with Tomek, so just easier to read the whole argument. Let me just remind you that we already talked about complementarily minimal Banach spaces. Complementarily homogeneous just means that if you have a subspace of Y which is isomorphic to X, then you can find a further subspace Z of Y which is complemented in X, and Z will be isomorphic to X. And all these spaces that I'm considering, they are all complementarily homogeneous. Actually, that the L infinity C lambda, this countably supported, the Banach space of countably supported bounded functions on lambda have this property that was proved by Bill, Tomek, and Gideon, I think. But for the rest, it was sort of known, I believe, but they reproved some of the other cases as well. So I will just denote all these spaces by the symbol E lambda. So lambda will just refer to the cardinality on which we're considering these functions. And again, I'm excluding the P equals infinity case. A result from, I don't know, 2015 or 16 from PAMS. So it's Bill, Tomek, and Gideon. They proved that for all these Banach spaces, the E kappa singular operators on E lambda form a closed non-zero proper two-sided ideal whenever kappa is any cardinal number, infinite cardinal number, sorry, which is less than or equal to lambda. And in particular, the E lambda singular operators on E lambda is the unique maximal ideal. Another thing that we'll be using in the proof, and they proved it, is that if both lambda and kappa are uncountable cardinals, where lambda is of course greater than or equal to kappa, and k is not the cardinal successor of any cardinal number, then you can write the e kappa singular operators on e lambda as the increasing union. Sorry.
Sorry to interrupt. Just wanted to make sure this factor I, E, kappa, E lambda. What do you denote by that mathematical I? The set I, E, kappa, E lambda.
I'll go back then a few slides. It's
sorry.
So it was defined. So this set was defined this way. So an element doesn't belong to this. So an operator belongs to this set if for any subspace which is isomorphic to Y, that was in the subscript, then that's not bounded below. So it's easier to define when it doesn't belong to that. So it was.
Thank you.
Yeah. Yeah, and it's a conglomeration of notation. I'm sorry, but yeah. So again, when K is not a successor of any cardinal, then you can write this ideal as the increasing union of the E lambda singular operators, where and the closure, you have to take the closure where alpha runs through, or the cardinal numbers, or the infinite cardinal numbers which are strictly less than kappa. And lastly, what we will need for this result is the following. So if lambda and kappa are infinite cardinals satisfying this, and you have an operator which is not E kappa singular, then actually the E kappa successor singular operators will be contained in the closed two-sided ideal generated by T. So again, if T is not E kappa singular, then you consider this ideal, which is the next bigger one, it will be contained in the ideal, the closed two-sided ideal generated by T. Now, so for L infinite, for this Banach space, this was included in the paper of Bill and Tomek and Gideon. It's not the LP cases and the C0 case is not written in their paper, but I'm pretty much 100% certain they knew about it because they put a result at the end of the paper, which presupposes that they know this. So anyway, let me just proceed. So we eventually would like to show that E lambda has the Psi property, and this will use these three results that I mentioned before, plus this dichotomy result and transfinite induction. And if I see it correctly, I have 10 minutes, Benjamin, or 11?
Yeah, that's about right. Yeah, 12 minutes. So 12 minutes, yeah.
Okay, so then perhaps there's time to show some parts of the proof of this. Yeah, so how do we prove this by transfinite induction? So this lambda will be some fixed infinite cardinal from now on, and suppose that E kappa has the Psi property for each cardinal which is strictly less than lambda. And again, as usual, assume towards contradiction that you have some infinite dimensional Banach space Y, and you have some surjective algebra homomorphism from B of lambda to By, which is not injective. So, of course, E kappa is isomorphic to a complemented subspace of E lambda, so take some projection which projects onto it. This will, of course, not be an E kappa singular operator. And therefore, by this theorem I had written above, we know that the E kappa successor singular operators will be contained in a closed two-sided ideal generated by this idempotent, which coincides with this ideal. This was the ideal of operators which approximately factor through E kappa. By the inductive hypothesis, we knew that this has the Psi property. So I'm going to use this second dichotomy result I had written previously to know that this ideal, this will be contained in the kernel. Hence, of course, with the other result, we know that the E kappa successor singular operators will be contained in the kernel. We will now prove that because of this, it must be true that the E lambda singular operators are contained in the kernel. As usual with transfinite induction, we're going to be considering 3 cases. So first, when lambda is just omega, then when lambda is a successor cardinal, and lastly, when lambda is some uncountable and not a successor cardinal. So the first case, actually, we pretty much already done that. So when lambda is omega, then E lambda is just either C0 or one of the LP spaces. And then we know by the dichotomy, the first dichotomy result, that the strictly singular operators must be contained in the kernel. And I haven't written it there yet, but actually, on all these Banach spaces, the inessential operators, the strictly singular operators, and the E singular operators are the same. So we have this containment. We can move on to the second case. So we are assuming now that lambda is actually the successor of some cardinal, the cardinal successor of some cardinal. Then, of course, we just have this because, sorry, I'm pointing with my finger and I'm not realizing this. So we had this containment, and if we assume that lambda is a successor cardinal, then this just trivially follows from that. So we have the very last case when lambda is some uncountable cardinal and it's not the successor of any cardinal. Well, of course, as I told you, then the E kappa singular operators will be contained in this one, which we know from the general machinery that this is contained in the kernel. And everything I said was true for each kappa cardinal, which is less than gamma. So we can take the union of all these guys and then the operator non-closure, and it still be in the kernel, because it's, of course, an ideal. And by this Bill and Gideon Tomac result, we know that this guy must be exactly the E lambda singular operator, so the claim is proven. But we again also know that this was the maximal ideal by the theorem. So we have this isomorphism at the end, and arguing exactly the same way, we know that this is simple because this is maximal, and this is not simple because Y is infinite dimensional. So we arrived at a contradiction. So we have that Y must be injective. In the remaining few minutes, let me just mention some other related results. So I haven't said anything about capital LP spaces. That's because I had no idea about the Shy property, but recently Bill Johnson was kind enough to communicate to me that they had solved the P in the reflexive range case with Chris Phillips and Gideon Schechtman. To my knowledge, this is not yet available, this preprint, or not yet published, but the point is that when P is in the reflexive range, then the LP spaces 0, 1 do have the Shy property. They also showed in this manuscript that some exotic complemented subspaces of LP have the Shy property, the Rosenthal subspace, for example. This Shy property has pretty much one nice permanence result, which is that if you have some finite set of Banach spaces with the Shy property, and you consider you add them up, you consider the direct sum, they will have the Shy property. Why is this relevant again? Just let me remind you that, for example, if you take LP plus LQ, where P and Q are different, or C0 plus LP, they have the Shy property by this result. But again, the bounded linear operators on this guy have very, very complicated lattice of close two-sided ideals, and I would like to refer you to the results of Dan Freeman, Thomas Schlumprecht, and André Jacques. But despite this nice fact, this is not, so unfortunately Chi is not a free-space property. This relies very much on a recent result of Niels Lausen and Piotr Koschmider. Niels was talking about this result at this very seminar, I believe. They showed that there exists some uncountable almost disjoint family under natural numbers, such that if you consider the corresponding Isbell-Mrówka space and the continuous functions on this locally compact space which vanish in infinity, then their bounded linear operators has a character. So on the other hand, so this is going on the one hand, and then on the other hand, it follows from the pretty much the construction that you can, this space is a twisted sum of C0 and C0 of the continuum. So in conclusion, we do know that these two spaces have the Chi property, but if you consider the short exact sequence, this sits in the middle, and this doesn't have the Chi property because this has a character. So unfortunately, it's not the free-space property. And I have 2 minutes left.
Yeah, a little more, actually 4 minutes.
4 minutes, great. Yeah. So let me just remind you, because so far I was very keen on telling you about spaces which have the Chi property, and I didn't really show you many examples of spaces which don't have the Chi property apart from pretty obvious ones. So recall that if X is such that V of X has a character, so it's an HI space, it's the James space, it's the Samadani space, then this doesn't have the Chi property because you can quotient onto the complex numbers. Actually, if you can take, you take finite sums of these spaces, then you can quotient to the n by n, the algebra of n by n matrices as well. But you know, you could argue that this is like, this doesn't really tell you anything. These people have done the hard work, and you know, this is just using their results, and I'm just quotienting onto something finite dimensional. So you might want to ask, can you quotient onto something infinite dimensional? So yes, you can do that actually. In fact, if you take any separable reflexive Banach space Y, and then you consider this Banach space XY, which is just the injective tensor product of C0 on, continuous functions on the half-open ordinary interval 0 omega 1 vanishing at infinity, and you injective tensor prod this with Y. You can also think about this as the Banach space of continuous functions on the ordinary interval to Y, which vanish at omega 1. So then you can construct a surjective non-injective algebra homomorphism from V of XY into V of Y, actually. And thank you very much for your attention. That's all I wanted to say today. Here are some sources.
Thank you very much, Bence. That was a beautiful talk. We can take questions if there are any.
Yeah, one comment. I think one of your early slides where you talked about the operators that are in the closure of the operators that factor through W, you neglected to mention that W should contain a complemented copy of its square.
Yes, yes.
And the reason I mention it is that this can be a problem even in some of the classical spaces. If you're looking at complemented subspaces of capital LP, for example, you don't know they have this property, and this causes some difficulties.
Thank you very much. Thanks, Bill. Yes. Where is it?
Excuse me. When you mentioned that LP lambda, lambda cardinality on which you consider these functions, does not have Chi property. What was the essential of? Sorry.
It does. LP.
LP on lambda when P equals infinity?
P equals infinity, I do not know if it has.
Yes. My question is, what is the essential obstacle which prevents L infinity on lambda have this shy property that kind of the surjective maps become injective?
So basically that I would need to understand much more about the lattice of close two-sided ideals of that guy. And I haven't mentioned it explicitly, but for the LP spaces where P is in the reflexive range of 1 or C0, and you consider it on any cardinal, this was done by Matt Dawes. It was completely characterized. I haven't used those results, but I sort of, or with Tomek, we used an alternative description for the LP spaces and this L infinity with countably supported functions. I think not the whole lattice is classified there, but everything from the above the weakly compact operators. And so for L infinity, the obstacle is also that you would need to understand, I think, all the, yeah, that it seems to be not really plausible to understand the lattice of close two-sided ideals there. That's.
Thank you.
Just a small query. The classical result of ideal height you mentioned in the beginning.
Yes.
Do we have something like an isometry analog of this result? If the given homomorphism is an isometry, then X and Y are isometric?
I do not know. I do not know. I don't know. No, sorry, I have no idea. I don't know.
Has it been studied? You have an idea? This question?
I actually think I haven't seen anything where the isometric version of this was considered for X. No.
Mm-hmm.
All right. Any other questions or comments?
I've got a question about the ideal heights result as well. It assumes that the algebras of operators in two infinite dimensional Banach spaces, say, are isomorphic in the Banach algebra sense as algebras as well as continuously. The example big LP and little LP, the algebras of bounded operators in that case are for any reflexive script LP space are isomorphic as Banach spaces, but they obviously can't be isomorphic as Banach algebras. Do you have any other examples where that can happen for infinite dimensional Banach spaces? I can't think off the top of my head of any that I can think of, but that's one that I can think of.
Oh, that's very good.
Hello.
We haven't.
I put some questions in the chat. Do you want me to repeat them, or you look at the chat?
Yes, please.
We are not finished with the other question. Are we done with the? Yeah. Okay. So the answer. Okay.
It's okay. The short answer is Hugh that I don't know. I don't know any other examples.
One example I can think of: big LP and little LP. And if you don't want to use ideal heights expression, the ideal structure has been considered for big LP and little LP. So they've got different ideal structures. So the algebras of bounded operators can't be isomorphic in the Banach algebra sense, but they are isomorphic in the Banach space sense. Okay.
Thanks, Hugh.
All righty then. So thank you so much, Bence. That was a wonderful talk. We'll still stay afterwards if you have like more questions or comments. So thanks a lot again.